All right, so hi everybody. Welcome to the first Papers We Love Boston meetup. I'm Bob, and this is Ashley. We're the co-organizers of the meetup. We work here at Boku, who has also graciously given us space and pizza and beer and not beer. So let's give them a round of applause. Boku does open web consulting and development and education, and Ashley and I are on the education team. She made me say this because she said I would say it better. Obviously, that is not true. So we're on the education team, and so we are interested in open education, and Papers We Love kind of caters to that itch we have. That said, this was a convenient place to hold it. If you would like to hold it at your place of business or recreation, and would like to sponsor a meetup or sponsor pizza and beer, we would love to have you, or not beer, we would love to have you do that. Talk to us afterwards. We would like to move this around a little bit so it's not always here. So, cool. Let's see. Anything else I was going to say? Awesome. We'll be filming this and it'll be up online later. So be on your best behavior. Thanks.
Yeah. All right. Clap for Bob. I'm really into clapping, so I think there should be tons of applause throughout this entire event. So as Bob said, my name is Ashley. I also work here at Boku and I work here on the education team. So just a little bit of background on Papers We Love. First up, raise your hand if you had heard of Papers We Love before the Boston meetup even started. Oh, that's really cool. Raise your hand if you've been to a Papers We Love meetup before. Very cool. Where?
It was the NoSQL Summit, which I guess is exactly the same concept.
Oh, interesting.
Germany,
Germany is really awesome. I'm really into Germany. So a couple of things that I wanted to tell you guys about this meetup. First and foremost, there's a code of conduct here. I hope you guys all read it. It's a paper I love. So let's just make sure to be nice to each other. If there's any problems, let me know. And then secondly, Papers We Love is supposed to be a very collaborative, very open source project. There's a GitHub repository, so if you search GitHub Papers We Love, you'll find it. Please contribute papers. That's something that everyone's looking for. Particularly, so this is like an international thing now. There's Papers We Love in different countries. There's Papers We Love all over the country. All over the country. And we're looking for a lot more diversity in the papers. And I can tell just by the RSVPs for this meetup alone that we have a really diverse audience, which I think is really awesome. So yeah, computational neuroscience, bioengineering, that stuff is all welcome, so please contribute. That being said, contributing papers is one thing you can do. We also are looking for speakers. I've already posted the date, September 18th, for our next meetup, and we need a speaker. So if you are interested in speaking, contact us. You can even make a pull request on the repo if you're really into doing it that way. But either way works. So that's what's up with that. So something that we've been trying to do is these types of papers often spark a lot of discussion, and linking to external resources and being able to talk to each other after and before the meetup is something that we want to facilitate. So the Papers We Love organization has started creating issues in the GitHub repo for every meetup that occurs, so you can check out other meetups there. And additionally, there is an issue, number 166, I believe, on the GitHub repo if you want to check that out and continue this discussion. So, with that being said, without further ado, our first speaker tonight is Christopher Meiklejohn. He is a senior engineer at Basho. What? I should move over?
No, you should stand in front of the camera.
Oh, I should stand in front of the camera. I wore a cute outfit just for this. So our first speaker is Christopher Meiklejohn. He is a senior engineer at Basho, where he also works for the Sync Free workshop, which is supported by the European Union. And he is also a grad student in the Georgia Tech master's program. He's going to be talking to us about a note on distributed computing, which is a Sun Microsystems paper, and I think he is definitely qualified to talk about this. So round of applause for Chris.
Hi, thank you. Thanks for the introduction. Oh, I guess I should. Okay. Okay, so I'm going to talk about a paper called A Note on Distributed Computing, which is, I guess it might have been internal when it was originally published in 1994 as part of Sun Microsystems laboratories. And there's quite a good group of people on this paper for sure. It's not a very, so preparing for this talk was really interesting because this was one of the first papers that I read on distributed computing, so I actually have no experience. I had no experience in distributed computing, like actually working on distributed computing systems, until I started at Basho 2.5 years ago. I did like a lot of systems administration stuff and things like that. So I read this paper without kind of the knowledge that I have now. Not going to say that the talk would be any better giving it now than it would then, because I've probably gotten more from the paper then. But it was a really interesting paper to prepare for. It was really stressful. I'm very nervous that the content is not going to be tailored for the audience correctly. I was at Papers We Love San Francisco last week, and Peter Alvaro, who's a good friend of mine, who's a graduate student at UC Berkeley doing a PhD in distributed computing and logic programming, presented this paper by Joseph Halpern about understanding like what knowledge is in distributed systems and reasoning about it. And his paper had 4 variants of modal logic in it. It had about 5 proofs or so in it, or they were a series of lemmas and then a major proof that outlined exactly how you could reason that common knowledge is unattainable in a distributed system, and how his final proof says that the 2 generals problem is unsolvable because the 2 generals problem relies on common knowledge. So in presenting his paper, he spent a lot of time trying to explain, like, you know, how you arrive at the proof, what the logic is, you know, what the various logics were, what you could express in those logics, how to read like formal semantics and things like that. It was a very hard paper. I don't think this paper is very hard at all if you have a background in distributed systems. I think the points that the paper makes are very straightforward. But what I think is challenging about this paper, if you're a first-time reader, how many people read it for the first time today, or for this meetup? How many people haven't read it yet? Okay. What I think is challenging about this paper is that he basically makes a lot of comments about like the kind of climate that the paper was written in. How many people remember CORV? Okay, wow, way more than I expected. That is fantastic. So, you know, in the front row we have the OG of CORV, Steve Banoski, who wrote one of the books on CORV. So he's here to correct me in case I say something really wrong about CORV or I critique it too much. So, okay. So here's the overview of the talk. We're going to do some background discussion about the thing, kind of what led us up to this point by the time this paper was written. Then we'll go through the paper briefly, and we'll kind of, you know, for the people who haven't read it, we'll talk about the high-level points. We won't really dig too much into the paper. And then we'll basically review where we are now and what languages look like today, and kind of where we've become and how we can avoid making the same mistakes that the paper kind of highlights. So again, I actually did an awesome introduction, so thank her for that. But I'll just reiterate what I do. So I'm a senior engineer at Basho Technologies. I work on React there. I work on multi-data center replication, and I do a lot of work on CRDTs, which are these fancy new distributed data structures that are kind of like in vogue at the moment, I guess, that help you reason about events in a distributed system. I'm a researcher with the St. Free Consortium, which is an EU-funded research project on distributed computing and synchronization-free computation. And I'm a former systems administrator, so I ran SGI, Sun Microsystems equipment, SGI machines, digital Unix in a previous life. So a lot of the things in the paper are very dear to my heart, I guess. And again, for the talk, we're going to kind of look at the motivations for the paper and not really focus. And I think the paper is very straightforward, but we'll go through the paper. But look at the motivations and kind of understand the history that brought us to this point and where we kind of are now, based on that this paper has been pretty seminal and pretty well read and heavily cited. 51 citations, 3 of which are Steve, which is pretty impressive. 1 of which is Roy Fielding's dissertation on REST, so we can kind of see how this whole kind of picture connects. Okay, so a timeline. So we're going to go back in time to 1974, and we're going to kind of work up to 2008, which I think is the most recent citation of the paper. And these slides have all the citations to all the papers that I'll mention in this talk, and you're free to go look at those if you're interested. And, I'm always available for any questions on any of those papers that you might have. Okay, so in 1974, look at these very low RFC numbers. In 1974, we had RFC 674. So RFC 674 basically defines something called, terrible acronym, PCP. I don't know why they chose that, but the Procedure Call Protocol, version 2. And this paper references a bunch of other papers which are basically very, very difficult to find at this point. They're probably on some machine in Ingenuity or something, on some backup tape. But it basically says that, you know, we want a mechanism to make procedure calls across the network, so that we can retrieve resources and kind of share our computing resources. And it's interesting because 1975, this RFC 684 is a commentary of the 674. So this one's very easy to read, and you can look at the commentary that this paper has. It's fairly long RFC, and this is the commentary on procedure calling as a network protocol. And this paper was done at Bolt, Barrick, and Newman, BBN, which became Genuity, one of the very, very early nodes of the internet. This paper actually cites the problem being that they need to share computing resources across all 70 nodes of the internet. So, oh my God. And 70 was a large number at the time, so that's very impressive. And, you know, this paper, and we'll talk more about the details, but this paper is kind of, this RFC is great to read, because if you read a note on distributed computing, you see that we've known about these things for 10 years. We've known about these things for 20 years, back to 75. The Waldo paper is published in 94. You'll see that we've known all of these things, but we just keep doing the same thing. You know? And if you read the note on distributed computing, and we'll talk about that, Waldo has a section where he says, you know, it's like deja vu. Every 10 years, we just kind of reinvent this thing and reinvent this thing, and we never really get what we really want. And every time we end up with a leaky abstraction, or, you know, some sort of model that doesn't necessarily represent like what's required of distribution in a network for a programming language. So moving to RFC 707, RFC 707 is very important because RFC 707 defines what would become Sun RPC. I'm sorry, I'm getting this confused. RFC 707 kind of defines what we want from making a protocol that machines can use instead of humans. So it examines telnet and things like that and makes some points about that. And we'll talk about the points that that paper highlights when we get into the meat of it. 1984, implementing remote procedure calls. This is the paper that basically defines Sun RPC, which is the first kind of major RPC mechanism that most people are familiar with if you've done any kind of network computing in the 90s. And then we have these two interesting papers that kind of come out right around the same time. And I think these are fantastic, and you should read them if you like programming languages and distributed systems. Distribution and abstract types of Emerald, and distributed programming Argus. So the Emerald paper talks about a programming language built on OpenVMS, so going way back. And it defines types that allow you to do distributed computing. And one of the things it focuses on is this idea of calling conventions call by move, which says I may have some object on some machine, and some other machine may want to do a function call that references that object, so I have to copy the data on the wire. And we'll see why this is interesting, because this approach is kind of taken in more contemporary computing languages. Distributed programming Argus is a paper by Barbara Liskov at MIT. She's very famous for her work in distributed systems. This is another fantastic programming paper about distributed programming, where you have these kind of guardians that live on nodes, and these guardians move between nodes. And as nodes fail, you know how to like bring these guardians to life on other nodes. And it says, well, the way we can handle this kind of idea of making calls across the network and stuff, and we want it to be atomic, so it has this idea that, you know, it looks like local programming. It says, well, we can do that by, you know, kind of doing coordination with rollback. Basically says every function call that you want to make that's going to be across the network has to have a rollback mechanism. That's extremely cumbersome for a programmer to write. Very, very hard. This is why databases and things do all this for us, right? And then in '88, we have RFC 1057, and this is the RFC that kind of really defines like Sun RPC as a standard. And this is your traditional, like, make a function call across the network, have some sort of stuff so you know how things work. And this is kind of what you see in things like Port Mapper, and Port Mapper that enables NFS and R login, and stat, like, what was it, like rstatsd was one there. Some of the RSH mechanisms, I think, eventually went to use RPC and things like that. Steve could tell you all about that. And then we fast forward ahead a bit, and we kind of work our way into the realm. So this timeline is kind of like function calling across the network. When we kind of move to timeline 2, which is 91 to now, we start looking at distributed objects. So this is what object-oriented programming is getting to be a paradigm that more people are using. We have CORV 1 comes out in 91. In 1996, this paper, Distributed Object Model for the Java System, which is also, if I remember correctly, written by Waldo, is the specification that defines RMI, so Remote Method Invocation, for Java between JVMs and later integrated with CORV. 97, you have CORV 2.0, which is like the big CORV release, and I kind of gloss over 99 to present because these are the things that most people are probably familiar with. So we have things like Enterprise Java Beans, XML RPC, I'm sure we all love that, and SOAP, which is really cool too, and then REST, which is what a lot of people are familiar with. So this is kind of the progression of object models and like kind of remote method invocation, the methods that allow you to do RPC for object-oriented programming. So what do we mean by remote procedure call? So remote procedure call is interesting because RPC is a thing. There's actually, Sun RPC is commonly referred to as RPC, like the RPC, but in terms of all the various papers that have progressed over the year, it's basically a general term for executing a submachine in a different address space without basically writing remote execution. So it allows you to say, I want to run increment on that object, or I'm going to call increment or new on this object across the network, and it basically takes care of everything for you. Again, the first popular implementation, so not the first implementation, there are things like DCE, Distributed Computing Environment. It's back when everything had very simple names like Distributed Shared Memory was a system, and like Virtual Machine was a system. So we have DCE was one, there was one at Apollo Computer, and Sun RPC being the one that most people know, because Sun RPC kind of was the model that you'd end up seeing in FreeBSD and OpenBSD and Linux and all sorts of things later that come. The later RPC mechanisms that you're probably more familiar with are Java RMI, like we just said, Modular 3 network objects, which is actually the inspiration for Java RMI. If you actually look at the documentation, Waldo was influential in both of those things and kind of moved this idea of network objects into the Java context. XML RPC, SOAP, CORV, some of the newer ones that allow remote procedure calls. So they're not always used for RPC, but RPC things that could be used for RPC, Avro and Thrift, and protocol buffers from Google. These are serialization formats on the wire. And then you have Finagle, which is Twitter's RPC mechanism that they use internally for doing these remote procedure calls. So RFC 684. So RFC 684, again, PCP. We say, so this is the critique of 674, which is the RFC that defines the procedure call protocol version 2. So see that here, and they basically say 3 points. 3 points. There's about 8, but it boils down to 3 important points. Is that procedure call is usually a primitive operation, so it's assumed usually in a programming language that procedure call is going to be a context switch. It's very primitive. It's very fast. It's kind of a change of control, and then you return to the calling function. When dealing with local versus remote semantics, these have different cost profiles. You don't necessarily get a return from your calls in the event of failure. We'll see that in the paper. And this idea of message passing, the ability to pass the message asynchronously and then get that message and then get a response later, is a much more valuable programming paradigm than doing this like call response procedure call kind of traditional function calling style invocation. So they basically talk about these 4 points, which will be very, very familiar as we go through the talk, which is, it's difficulty to recover from errors. Do you roll back How do you know if to roll back? How do you handle failures on the network? Do you raise an exception locally? What do you do? It's difficult to sequence operations, usually because you have some blocking semantic on a call. So you'd say, like, perform this function call, I'll wait, I'll get the response. So it becomes difficult to sequence things on the wire. Synchronization, again, is, synchronization is geared towards this call return kind of model. You make a function call, you wait for that function call to return a value, and then you continue executing. And finally, back pressure and load shedding. So back pressure is the ability to block on a subsequent action happening to enforce like systems so that they don't overload. So it's a type of overload protection. Load shedding is an alternative overload protection mechanism that says we'll drop it on the floor. These mechanisms become very, very hard, as well as with priority servicing. So priority queue mechanism for the function calls. If you wanted to enqueue a bunch of things and maybe drop some of them and handle them in priority order, a lot of these things become a bit more difficult to do with this call response kind of protocol. It's not saying it's impossible. It's not as, it's not as easy necessarily. RFC 707, which is, talking about generalizing this mechanism, observes that, and here's a quote from the paper, because of this cost differential, the application's programmer must exercise discretion in his use of remote resources, even though the mechanics that they use will be greatly simplified by the RTE, the runtime environment. Like virtual memory, the procedure call model offers great convenience and therefore power in exchange for reasonable alertness to the possibilities of abuse. So this paper, this RFC basically says, let's look at Telnet. Telnet is, and they make a great argument in the paper that says, I remember in the RFC that says, like, Telnet's really hard to share resources because, a person has to type everything, and, like, you don't know what the remote system's commands are going to be. And it's like a very, nowadays we're like, oh, it's a Unix machine, I'll just SSH into that and do something. And, like, in this, they're kind of like, well, hey, that's, like, really crazy. Like, you need to know the commands to run on that other machine. Which, we don't even think about that anymore. Again, we have services to allow us to share resources outside of that. And they say that, like, Telnet and FTP have this request-response cycle where you say, like, do some command, some parameter, like, get the response value back. SMTP, same thing, right? Hello, like, hello. FTP, like, there's switch it to binary mode, or, like, put a block, So they say, well, we need to make this more generic. How can we do this? So, you basically build a request-response mechanism. That request-response specifies a procedure. That procedure takes arguments. That procedure and that call have an identifier. And so when you get your response, you know which request it was for. But again, RFC 707 says, well, I mean, look at this other stuff. All these control flow things about how to do priority servicing and back pressure and all of these things, all of these arguments that we made here in RFC 684, they all still hold. Needless to say, we still move in this direction. So you see that there's common themes coming up. People recognize that there's all these downfalls and all these things that don't necessarily map correctly. And there's basically an impedance mismatch. But we continue moving forward. We keep doing these things. And you'll see, again, that this is going to be a common theme of the paper. So distributed objects. So distributed objects are referenced in the paper. They specifically talk about distributed objects. So distributed objects can be two things. So we're going to make it clear what we're referring to and what they're referring to in the paper when they say distributed objects. So the first type of distributed objects are replicated objects. These are not the type we're talking about. They could be replicated, but the replicated as it's commonly known today are the things that you see in things like state machine replication, where you basically send the same request to a bunch of state machines and you achieve fault tolerance through state machine replication. So sometimes you'll see replicated objects referred to as that. That's not what we're talking about. Again, if you're familiar with Ken Berman's work at Cornell on ISIS or virtual synchrony, these also refer to as replicated objects. These virtual synchrony uses state machine replication essentially. Process groups from ISIS are basically groups of coordinating workers who might get similar messages that can take over for each other. So process groups are another mechanism for fault tolerance, commonly referred to as distributed objects. We're not talking about those either. What we are talking about is these idea of live objects. These live objects are basically distinct identities. If you think of an object-oriented programming language, you have some object. That's the type of objects we're referring to. Actual, like, OO-style objects. Each of these objects has a distinct identity. It's got a memory location. It's got all that stuff. They encapsulate their own state. They have methods. You invoke methods on the objects. We're talking about traditional style OO programming. An example of this is CORV and DCOM. So we got a show of hands for CORV. How many people remember DCOM? It's a smaller crowd, but similar. So CORV, we'll talk about. DCOM, we're not really going to talk about it because it's very similar. It came a little bit later than CORV. DCOM was basically Microsoft's COM distributed. DCOM. So CORV. So CORV is the Common Object Request Broker Architecture. What a crazy name. What is CORV? So CORV is basically an abstraction that allows you to communicate between different languages running on different machines in different address spaces. CORV was very big in C++. There's some CORV in Java. There's CORV in all sorts of languages. If there wasn't a native implementation, there was a way to write these things called orbs that allowed you to integrate other languages. So if you really wanted to do CORV with Tickle, you could write an orb for it. There is one. Steve probably wrote it. But who knows? You probably wrote a lot of them, actually. So how does CORV work? So it uses an interface definition language, or an IDL. This IDL allows you to specify for classes of objects what the interface for those objects are. So you'd have this thing, it would be a stub that allowed you to say that a remote node was going to be able to accept like calls for particular things. So it's basically an interface, just an interface thing. And then what you do is, in your programming language, you map these IDLs to actual implementations. So you say that this maps to this implementation of this function call, of this implementation of this object in C++. So you can have something in C++, talk to something in, I don't even know, give me some Pascal. So what were the supposed benefits of CORV? Was that a lie? It wasn't there Pascal? Yeah, all right. So what were the supposed benefits of CORV? So language independence, right? You could have a bunch of different languages, a bunch of applications written in different languages, and all of these could talk to each other. OS independence, hardware independence, like architecture independence. You could run whatever infrastructure you wanted, whatever things you wanted. They could all talk to each other. It's like a brave new world we're entering here with CORV. It also had typing, which is cool, right? So you could specify types. You could say that messages on the wire were going to have this particular type, and those types got mapped into local types, and you could enforce type constraints. And data transfer. So it had the ability to move an object while the system was running, from a local node to a remote node, and nobody's knowing where the object is, can be anywhere. They can move on the fly. That's not really super straightforward, but these are the promises of CORV. So in 2003, Steve Bronowski, for the IEEE, for an IEEE journal, wrote an article called "It's Just a Mapping Problem." And the quote here is, "The goal is to merge middleware abstractions directly into the realm of the programming language, minimizing the impedance mismatch between the programming language world and the middleware world. For example, mappings make request implications on distributed objects, and services appear in normal programming language function calls, and they map distributed system exceptions into native programming language exception handling mechanisms." So, the promise is that you can just make these function calls. They'll happen across the wire. Things will happen. If there's a problem, it will raise an exception locally. And everything looks like it's local. You can basically do all of your distributed programming like it's on your machine. And then a lot of the arguments for things like CORV, and this is what Steve argues in his paper, is that programmers are validating how well these systems work, like CORV and DCOM, based on the transparency of the language. Like, how well it transparently allows you to do all of this distributed computation. But the problem is that's not always the correct answer for building software, and it doesn't necessarily always lead to correct software. And this paper that's written in 2000, this article that's written in 2003, directly references the paper that we're talking about tonight. So Waldo, a note on distributed computing. All right, so let's talk about the paper. So this paper basically says, and this is kind of the core statement of the paper, is the thesis of this note that the unified view of objects is mistaken. So Waldo kind of says that, to treat local objects and to treat remote objects as the same is like fundamentally flawed, because local versus distributed, as it's called in the paper, distributed versus local computing are completely different things. And distributed computing has some very, very specific fundamental problems that local computing doesn't have. He basically says, you know, if you ignore this, you know, we keep repeating this mistake. If you ignore it, it's bad. Your applications are not going to be correct. And he references these two works as well. So he references the historical works of Emerald and Argus, so these two distributed programming languages that allow you to, you know, transparently kind of work with objects that are located across the network. And then he, you know, he references Corva. I mean, this paper, if you read it under the Corva context, you realize that this paper is an attack on Corva. I mean, it's straight out an attack on Corva. Corva is referenced once, but I don't remember the exact line, but it's not like, it's not super favorable, but it's not super negative to Corva. But essentially, it's a critique of Corva and all the work that was happening in Corva at the time. So he defines these like objects. So objects are interfaces defined in an IDL. So we talked about what the IDL is. So the IDL is essentially that mapping layer that allows you to have these stub objects that you define the interface for the remote objects that you're going to call, and then you basically build the implementations of these objects on all of the things that implement them. And you know, he acknowledges that this is clearly an application of the remote procedure call like paradigm to object-oriented programming. It abstracts out all of the communication. So these things abstract out all of the communication overhead, how to contact the nodes. It knows how to contact nodes. It knows where nodes are located. It knows where these objects are located. You don't think about any of those things. And again, this you're reading the paper like, yeah, that makes a lot of sense. Like that doesn't make, why do these people think that? Again, I mean, we've learned this already, right? We have these previous RFCs. We have the problems with Sun RPC. We have all these commentaries, RC 684, 707. We've already kind of, like, by the time we get to 94, and we've already observed these things happening in the real world. They were originally critiques and RFCs from 20 years prior. So these are all things that we already know. In his paper, he kind of says, well, what's the promise of this unified view of objects? And the promise is that, he breaks it into 3 stages. He says that, you should be able to write a program and get the interfaces correct, and focus on just on your local machine, getting those interfaces correct, and building the application, assuming that you get all of your objects right and know how they're all going to interact and write all of the interfaces. And then you can tune performance by figuring out where objects should be located to understand how they interact. And in the paper they talk about this like mythical tool that doesn't exist that it'd be nice to have to be able to allow you to examine how objects are interacting, so you know where to locate those objects across the network and on machines. And then he says, like, yeah, well, we'll test with real bullets, right? Like, we'll figure out how to partition the network. We'll figure out how to make partial failure. We'll sort it all out, and the interface will kind of just fall out from that, right? Like, the testing will tell us where things need to be hardened and things like that. And, we know that this is wrong. Like, we know that this is fundamentally wrong. Maybe at the time we don't, but at the time, people are disagreeing with it. But it's been said before that, these things are hard. And, you look at software that's developed today, you look at databases especially, like, we're constantly finding problems with it, right? I have people here read Kyle Kingsbury's blog, right? Peer review, yeah. And Kyle Kingsbury's blog is a classic example. We just keep finding these things, right? Like, something just makes no assumption about, oh, I can just make some call over here and wait for it and whatever, everything will be fine. We have these problems with databases. We have these problems with consensus algorithms. We have these problems, like, there's all sorts of these problems. And it's pretty naive to think that, I'll throw a couple network partitions at it and I'll find all of the problems, right? And we know that that's a naive approach today, because if you look at the work of things like Concur and Pulse and a lot of the quick check work, and especially the field of model checking and formal verification, we know that, like, we can't find these things just by kind of, throwing a network partition at my software, running the thing once and saying, hey, all right, you withstood the failure. That's great. So he kind of identifies these 3 false principles. So there's a single natural object-oriented design for a given application. So they say that, you get the interfaces right and everything right, and, the location of the objects doesn't really matter as long as those interfaces are right. And those, keep in mind, those interfaces are defined on a local node. Now, there's failure and performance issues are tied to the implementation of components of an application, and the consideration of these issues should be left out of an initial design. Again, it's pretty clear that that is false as well. And he goes to prove a lot of these points in the rest of the paper. And the interface of an object is independent of the context in which the object is used, which is pretty clearly false. So this is a fun part of the paper. So this is the part where he talks about the language approach. So this is in the deja vu section. You know, he says, clearly, the hard problems of distributed computing are not the problems of getting things on and off the wire. And we know that's true. The hard problems are the partial failure, it's concurrency, it's all of those things like that, memory access, latency. And he has this thing, he has this quote where he says, well, every 10 years, you know? Every 10 years is a programming model that everybody's using. We see that nobody's writing distributed applications, so what do? We try to basically adapt distributed computing to the programming model that we have today. We find out that there's an impedance mismatch. It doesn't really work, and then, you know, distributed systems evolve, programming languages evolve, and we kind of just go through this battle again. So, you know, it's cautionary tale here. But, and, you know, again, they highlight failure stems from the inherent differences between local and distributed computing. So he highlights the problems, and, you know, I think he really didn't, I think I added a few maybe, but, you know, we have latency is a huge problem, coordination is a problem, partial failure is a very big problem. Anybody in distributed systems and databases know that partial failure is really difficult to work with. Memory access, that's kind of very related to the distributed objects notion, because it's not very applicable. It's not super applicable when looking at functional programming languages and RPC calls, but it is in some cases, and we'll talk about when that's true. And finally, concurrency. Okay, so latency. So we all know latency is a problem. This is really obvious. It's not fundamental. Calls are going to take longer when they go across the network. That should be pretty easy to reason about. It should be pretty clear from just working with your computer every day that things across the network are slow. Ignoring latency will impact performance. If you write an entire application locally and you assume that everything's going to be fine when you put it on the network, you're going to be wrong. We experience this every day at Basho, for sure. You probably experience it in all of your applications as well, if you're developers or not. And, you know, again, this is like kind of the, you know, there's a concurrency argument here too, and this is like, you know, we'll rely on things increasing in speed. But yeah, that argument doesn't hold up at global scale. It doesn't hold up on networking with congestion. We see things all, you know, sure, hardware is going to get faster. We're still using TCP, right? So like TCP is still going to be a problem. You have things like TCP slow start. You have things like, you know, all of the congestion control mechanisms. You have problems like TCP incast. It's like the network can collapse, and it doesn't matter how fast your hardware is. It doesn't matter how fast your switches are. Like certain network conditions will always make the network collapse. So I mean, this is like a total fallacy here, you know. And we've been dealing, you know, there's tons of arguments on programming languages that, you know, are you know, arguments for Erlang or things like Go or Rust. You say, you know, well, we're getting more cores, the processors are getting slow. It's the same argument, right? And again, this idea of like, well, we can use, again, he references the mythical tool, right? Like, we can use the tool and we can look at the objects and we can say, well, you know, these two guys are communicating, so, you know, we can co-locate those on a particular node. Again, are those conditions going to hold true all the time? Is the access pattern always going to stay the same? You know, the performance analysis in itself is complicated, and you know, this like you can't always just move things around. It's not always practical, and it's kind of naive to think that that's a valid approach that you can take to building a distributed system. So the memory access section of the paper. The memory access section is pretty much related to, so this is directly related to CORV and C++. In C++, you could have objects. They could have pointers to other objects. That object would be in a local address space, potentially. You know, one approach to solve this that they highlight in the paper is that you can use distributed shared memory. Not many people use distributed shared memory. And there's the idea that you can do this replacement of references. So this is an interesting part in the paper because it's like it's not very clear what he means by replacing pointers with references. But in the CORV sense of the world, you have you basically have CORV references that allow you to say, well, this object is located on this machine. I have to go to this IP address on this port to contact that object. So it says that, you know, in the runtime system, you could replace all of those references with CORV references. But he says this thing, like, he makes this argument like, well, you know, it's like a permit versus enforce argument. You can't enforce it because the language is still going to let you have address relative pointers. And, as soon as you do that, you've basically created something that's going to either not be correct or not work. And he highlights marshalling here, so I wanted to highlight the use of marshalling in this argument is, as you'll see later in RMI, is directly related, is not just serialization of the object. So in languages like Ruby or Python, marshalling and serialization are basically equivalent. For the most part, in Python they definitely are. In Ruby, I believe they are. There's a difference between serialization and marshalling, where serialization is like, packing the object in a format for the wire and sending it across, and then basically building it back into the object. In the Java sense of the word, marshalling, it's actually shipping the code. So you would actually ship the entire code over, so that even if the remote node didn't have that object class, you could basically invoke it and load that object back up and work with it there. And this marshalling also involves, taking referenced objects and sending those things on the wire too. So it's not, it's non-trivial to do this, and it's not trivial to do it in a way where you make it safe to program, because you'll always have those backdoors where you can do things. You can't really prohibit it, unless you do it in the runtime or compile time or something like that by switching out the portal reference. Cool. So partial failure and concurrency. So this is kind of the fundamental difference between local and remote computing. So in local computing, if you go to make some call to a function on the local machine, you happen to switch control and execute that function, locally failures are going to be total. The majority of the time they will be total. You'll usually get a return back from the function, you'll get a failure, and you can be sure that the global state is in it. Usually, depending on, there are some cases where you could argue that it's not, but the global state will be intact. And there are mechanisms for controlling this concurrency and things like that as well. So in local computing, things are total. Where in distributed computing, we don't have any of these guarantees. Partial failure is the idea that I go to run some operation on a series of machines, or even a single machine. I send the request. Maybe the machine fails, maybe the network fails. You don't know if that update was applied or not. It could have been applied. The state could reflect that change. It might not reflect that change. If you're familiar with databases such as React, which is the one that I work on, or Cassandra, or things like that, we write to a quorum of nodes. Partial failure is the situation where you say, I want to write this value to a series of nodes, and it writes it to some of them, fails on the rest, and then you either get a success or response. You don't know whether that value was really written. You don't know if that value is persisted to disk. You really have no way of knowing. And this is in asynchronous communication specifically. There's not really, global state isn't the same as when you're doing local computation either. And there's this core idea here is that the failure of a link is indistinguishable from process failure. And you'll see in things like in the FLP and possibility result, which is about distributed computing, they highlight some things where, in asynchronous networks, if you send a message, you have no way of knowing if the remote party, unless you send a message back, you have no way of knowing if the remote party received that message, the remote party is even still alive. You don't know if, you can't distinguish the non-existence of something from an infinite delay of something, right? So these things are really hard to reason about in distributed systems. So to think that local computing is the same as remote computing this is where the fundamental difference is. So here's a quote from the paper where he says, the question is not can you make remote method invocation look like local method invocation, but rather what is the price of making remote method invocation identical to local method invocation. So these things are kind of core problems in distributed computing. This is kind of, you could think of this as the consensus problem, right? This is the consensus problem, this is the agreement problem. You could, basically stop the world. I'm going to execute this function. Everybody's going to wait. Wait till the results there and do it. You could do that for everything. You would never make an application that anybody wanted to use because it would take forever. You can't even guarantee termination in some cases without timeouts and things like that. So he says that there are basically two possible paths to a unified object model. And this is the kind of dichotomy he talks about in the paper a lot, is that you either treat all objects as local, or you treat all, and you have these, you have something like CORV do your distribution and things like that. But the opposite approach is that you treat everything as remote. But the whole premise of the unified object model is to make it so local distributed computing is as simple as local computing. So to make everything seem like it's remote, then why bother, right? It defeats basically the purpose of things like CORV and DCOM and things like that. Oh my God, look at that egregious typo on my slide. I'm surprised somebody hasn't tweeted about it yet. So concurrency concurrency shares the same problems. So concurrency has the same problems that partial failure basically has. And he highlights all these things. And again, with concurrency, you say, well, if one of those objects, this object that's transparently can be on any node, is going to do some concurrent work and has to be available for concurrent requests, then basically all objects need to have that logic, right? Because you never know whether that's going to call some other thing or another object's going to become one of those objects. You basically have to treat all objects like they're going to have concurrency. So you're back to this idea: do we treat everything as local, or do we treat everything as remote? So Jim Waldo says it much better than I can, and he says this approach would defeat the overall purpose of unifying the object models. The real reason for attempting such a unification is to make distributed computing more like local computing, and thus make distributed computing easier. This second approach to unifying the models makes local computing as complex as distributed computing. Well said, Jim. So I really like this part of the paper. This is one of my favorites because I think this is very applicable to distributed systems. If you work with any of these things, if you work with things, basically any database or any kind of concurrent language, these things are really, really interesting. The problem's highlighted here. So they define this quality of service metric is based on the implement, how well it handles all of these things, how well the distribution works and how well it handles partial failure and all sorts of things like that. So they give this example of a queue. So they basically say, I'm going to have some object that's going to represent a distributed queue. It's going to represent a queue. You don't know if it's distributed or not, right? That's the whole promise of the paper. And you're going to insert things, you're going to in-queue things, you're going to de-queue things. So the example they give is, all right, I'm in-queuing a bunch of things, and then I get a timeout operation. And they get a timeout operation. So how do I deal with this timeout? So I'll retry. So they're like, well, let's just retry and queuing. I get a timeout, I'll try it again. Try it again. And what they're saying is this is observed partial failure in this example. So they end up noticing that they're dequeuing objects more than once. So, oh man, I dequeued that object, I have another problem. And the idea is that there's a partial failure, right? You get this timeout, but the operation succeeds. So how do you reason? How do you know? How do you know if that operation actually went through or not, right? And they say, well, I should have used the component that avoids duplicating objects, but the interface doesn't, have that. And I think this is a good parallel to something that we talk about in distributed computing, which says that you have a bunch of these components, and each of these components makes a specific guarantee, but those guarantees don't hold over composition. So this is a very interesting thing in distributed computing now, and distributed computing research is you say, well, I have, Kyle wrote an article on Kafka. You don't need to know what these things are, but he wrote an article on Kafka, which ended up using Zookeeper, which are these two different services, distributed computing services. And, Kafka, makes some sort of guarantees, and Zookeeper makes some sort of guarantees. But when you compose these two things and use them together, none of these guarantees hold. The system basically falls apart, and you have some violation of causality. And so this is kind of clear here too, right? Where you say well, I do this I perform this operation, I assume some guarantee is going to happen, but you don't really get that, right? And this queue, while you might have tested it locally, might have worked fine, right? But as soon as it gets distributed over the network, the entire thing falls apart, and you start having these problems. And now, this idea of, well, I'll put a unique ID in there, so when I dequeue, I can basically de-do. Well, now you're keeping track of objects. Now you're basically just writing the distributed code that the object should have had, right? So again, we're well, model didn't really match up. So we'll just start writing the code that we probably should have written in the first place to do this stuff. Or use a strongly consistent queue is another option. But that's being very explicit. You're opting in to use a distributed queue with coordination, right? So the transparency's gone at that point. The second example they gave is this idea that you want to query something, and you want to, as long as there's a value in some set or some context object, you're going to keep deleting that value. And then once it's gone, you'll move on. So your program basically like loops and says, well, as long as this thing's in here, I'm going to delete it. And then as soon as it's gone, I know my program can move on. So like without locking, without coordination, like there are race conditions, partial rights, you name it. Like this, I mean, we are still struggling with this problem here today. Causality is difficult, right? Like if in the event that there's a concurrent addition to that set and a concurrent removal to that set, those things can be observed in any order, right? You have no causality, you have no way of knowing which influenced the other operation, right? And these things could be delayed on the network. You could say, well, if nothing was in there. Oh, there was a network partition. This guy came back, now it's back in there, right? You could say, well, remove this thing. Oh, there's a delayed message on the network. Like, then it shows up again. You could say, delete this thing. Some other guy concurrently deletes it and then re-adds it. Well, now you've deleted his addition into the set, right? So causality is really, really hard. And we fight with these things every day. Causality is a huge problem in all sorts of distributed databases. It's huge problems in distributed queues, programming languages, all sorts of things. Like causality is a very rich subject if you're ever looking for something to explore and you like reading papers by people like Leslie Lamport. This is a good one. And the two papers I reference here are absolutely fantastic. The first one is Time, Clocks, well, I don't know the order of the bit tech here, but it's Time, Clocks, and Ordering Events in a Distributed System, which is the classic like 78 Lamport paper where he talks about how to characterize causality on a network. And then the second paper is the Sharon Boast result, where Bernadette Sharon Boast talks about the idea that there's a minimal subset of information needed to properly characterize causality, and basically looks at things like vector clocks, all of the mechanisms that we use today, and say, well, all of these mechanisms are lossy. And really, you need causal histories, and that's what Lamport talks about in this paper. So it's like fascinating to read about, because it makes you think about events in your programming language and your application in a completely different way. Yeah, so as you could tell, that's like my favorite topic. But yeah, so whatever. So anyway, so so the section on NFS is amazing. It doesn't actually contain like any details about NFS, which is awesome, because it definitely drives home a point without putting really any details in there. So how many people here are familiar with network file system or ever used it? I mean, most people who went to college probably ran network file system if it was in the 90s. Network file system is terrible, but it's amazing in the same way because it was like the first distributed file system. So like NFS traditionally only ever returned errors when something really really horrible, like the worst possible situation happened. Like the disk was full and it couldn't run anymore, or like the disk was gone, right? Like, oh god, like dev SCA is no longer there. Like, holy shit, it's a really bad problem happening right now. So like all of the errors were catastrophic, like the system is going down type things. The problem is that when you start using NFS with it, you introduce a whole new class of errors. Partial writes, unavailable nodes, network partitions, all of these things, right? So NFS basically has gone through 4 versions. NFS 4 is the current version today if you're looking to set up NFS tomorrow. It's a stateless protocol implemented in UDP. So it's a stateless protocol specifically done that way because they felt that it was easier to debug. If you aren't shipping state around, the class of errors is much smaller, much simpler to work with. And Jim Waldo kind of says, well, look at peer-to-peer applications, which are basically like any of these distributed databases we use, BitTorrent, Bitcoin, all these things. You look at all these peer-to-peer, CORV is another one. You look at all of these distributed applications that are peer-to-peer, like it's much harder to reason about the state of things because now you're worried about like whether like you have all these network problems, but you also have all this state. Like, how do I keep all this state up to date? And this is like why we have things like consensus algorithms and agreement protocols and things like that. So NFS operates in 2 modes, soft mounting or hard mounting. So if you've ever used NFS, you've probably used it in the hard mounting mode. Soft mounting basically introduces all of these new error numbers and error codes, none of which your application probably knows about. This is a huge problem if you get a message like, the node across the wire has some sort of like disk error or something. And you say, okay, like the write succeeded or something. Those kind of things are really bad. So yeah, don't add things to protocols without versioning them is the lesson there. And I'm sure there are plenty of people, I have plenty of stories about that. So yeah, don't do that. And again, it's like, it's problematic, right? You're not going to go back. You're not going to do these things. You're not going to update all of the applications. Sun for sure didn't. Then again, that was like, the bold era before, that bold era of like Sun freeware and packages and things like that. So again, when Sun didn't even come with like a compiler that works. So, and then you have hard mounting. So hard mounting basically says, well, we're going to keep all the error codes the same, and we're basically just going to block. So if you've ever used NFS, I am very familiar with this problem as somebody who worked in telco with NFS deployed over many states. You have the situation where like you CD into a directory and you do ls and it hangs forever and you have to kill your terminal connection. That's a super fun one. It's really awesome, especially like because you're probably using Telnet at the time too. So get that password on the wire a few more times. So yeah, application hangs. Basically, NFS pauses. And this is the most used mechanism. And this is clearly what we've been talking about, right? This idea that we're treating the remote resources local. It doesn't work. You are not accounting for all possible failure conditions. So Jeremy, like, this is a weird section of the paper because, he just kind of argues that, like, if you want to use these IDLs and you want to have these this sort of unified model, you have to be explicit whether something's local or remote. He says you have to be aware of it. The programmer has to know about it. The programmer has to opt in, knowing that I have to handle like a partial write problem. I have to handle latency issues and things like that. But he says just make sure that the programmer is fully aware of whether this object is local or remote. And then there's some CORV-related things like, well, you could generate different definitions if it's local versus remote, and you can know these things at a particular time. So there's a bunch of CORV-related specific stuff. But the general idea is that you have to be aware of the problems. So we're almost at the end of the paper, and then we'll kind of talk about some languages today, and then we'll be done. So very shortly, about 10 minutes probably, maybe 5. So the last section of this paper, there's not really a conclusion to the paper, which is hilarious. There sort of is, but there's not really a summary. Because the last section is on a middle ground. So he identifies these objects in the first section of the paper that says, you're going to have some objects that are going to have local remote semantics, right? They might have higher latency, but they might be on the, the memory might be available to all the nodes, might be shared. And he identifies 2 programming languages, Clouds, which is referenced in the beginning of the paper, and he also references Spring. So I'm not going to talk about those because you guys don't really care about those languages. And you're not going to use them today. So what I think is the best analog to talk about these local versus remote objects is the idea of NUMA. So is everybody familiar with NUMA here? No. Okay, good. Should have put more in there. Damn, I just played about half of the things. So NUMA is non-uniform memory access. So it's basically saying that you have memory that's located closer to processors for better performance, essentially. So if you happen to write something that's going to read something out of an array, and that array is located, they're called NUMA nodes. If that array happens to be located in a piece of memory that's for this processor way over here, you have a higher cost. So it's the idea, it's kind of like the cache levels applied to processors, essentially, like moving the memory around in the same way that we deal with different cache levels, like L1 versus L2 cache, and the penalties that we pay for moving data between the different caches, right? So NUMA is interesting because you can have a totally different cost profile on reading an object that is local than reading another object. So NUMA is the case where you do have these kind of local remote objects. You don't have to deal with partial failure, but you have to deal with the fact that a call might be really slow making it to another NUMA node. This is something programmers have to be aware of. This is a thing that's becoming very, very important because this is how you get high-performance applications. Some languages are trying to do things in the runtime. Steve could probably talk about this better, but I think Erlang is trying to be smarter about NUMA. But it becomes more difficult when you have shared objects. Because shared objects, where do you locate the shared objects? Do you never put them in any of the optimized memory locations, or do you always put them in some memory that's equal path for all the nodes, or what? So NUMA is a very good example of why we have to be aware of these things and sometimes treat things differently. And we'll see what happens with NUMA. A lot of programming languages and compilers are trying to be smarter about allocating memory so that things are located in the right places. But that's saying nothing about a language that not everybody's going to use, GHC Haskell, the one that came out last week. People are going to be programming on I don't know, C++11. That's a bad example because that's new too, but you know, whatever the one was before that, right, Steve? C++98, whatever. I don't know. Okay, so anyway, moving on. So Steve, again, I will say Steve. He's you know, he's basically the pinnacle. He's the end and the beginning and the middle of this talk. It's amazing. So Steve says in his paper that he writes at the IEEE journal in 2008 called "Convenience Over Correctness" is a fantastic article. I highly recommend all of you read it. It's available on Steve's webpage. Says we have a general purpose imperative programming language hammer, so we treat distributed computing as just another nail to benefit the programming models. And Steve makes a couple of interesting points here. So he goes through the history of this RPC thing this RPC timeline dance that we did at the beginning, and he cites the Waldo paper again, saying that you know there's a bunch of things you have to watch out for, and they've already been identified as by Jim Waldo in '94, as well as some other people earlier. And he says. He has two major points and then talks about like a brave new world, sort of. And the first point is that, again, there's this impedance mismatch with the IDLs, right? The IDLs allow you to map from these remote things into these local things. And these IDLs allow you to say, you know, I have a Java object, a Java set, and I'm going to communicate with a C++ set or something, right? And it's that you have to map between these. But the problem is that for primitive types, just like integers, you know, integers, booleans, things like that, those types are easy to map because in each language, those things have primitives that you can use. You can map into them easily. But it gets a bit more complicated when you start doing like, hey, I'm using that Java like util graph structure, and like, you know, I'm going to send this to my C++ app. Well, what do I do then, right? Like, how do I even get this across the wire? So there's this idea that as you start building these more complex applications, like the ability to map between these types becomes a lot harder, and basically. This causes this impedance mismatch that makes the models not really work together. Again, there's this, the second point he makes is this idea of scalability. So latency is a huge, you know, it's a huge issue. Usually, when writing a large-scale application, you want to use things like caching. You want to know when to cache values. You want to know when to read from that cache. You want to know when to evict from that cache. You know, the general idea of having a remote procedure call mechanism where I say, hey, I'm going to go across the wire and call this function over here, and I'm going to get the result, like, that says nothing about whether the value should be cached. Like, our function calls don't have any of this information in them. Should I cache them? When do I invalidate it? How do I know how to invalidate it? How do I know when it should be invalidated? All of these things don't exist in RPC. And, you know, there have been attempts to basically add metadata to these calls or add metadata to the objects to basically influence how these values should be treated. But, you know, again, the model doesn't really match up. So he talks about REST, and, you know, REST is a good mechanism. REST is a mechanism that models distribution, right? It doesn't model, it models resources and distribution and how to cache these things. A bunch of the verbs in HTTP that REST use have, you know, semantics associated with them that you know that, like, hey, a get is supposed to be idempotent, so my app knows that it can do that a million times, and it doesn't have to worry that it's like causing a side. Like, I'm not getting and firing a missile, right? You could implement it that way, but that would be on you. But the idea that, like, you know, if we just try to build an object model on top of REST, well, we're kind of getting back to the beginning of the paper, aren't we? Like, if we're going to just build an object model to fit on top of REST, we're going to be fitting a object model to, we're going to be fitting a distribution problem and a distribution framework to an object model. And again, we'll probably run into some of this. I'm not saying that you won't be successful. It might be very successful for you, but it doesn't really match the problem, and you'll probably find a situation where something doesn't end up being correct. So we'll kind of look at like distributed languages today. So what do I mean by distributed languages? So I don't mean languages that can do network stuff. I mean languages that have distribution as first class. So the languages that we'll talk about are Erlang inspired or Erlang. I'll pitch Erlang. Erlang is a very favorite language of mine. I write in it every day. So Erlang has an RPC mechanism. We use it in React. We're idiots for doing it. True. But it prefers asynchronous message passing. And RPC in Erlang is implemented as asynchronous message passing, where it sends a message and it waits and there's one coordinating process for every message. It goes through a server called Rex, the remote execution server. It's bad. You shouldn't use it. And Erlang has adopted this, it's adopted the second thing of Waldo's paper. They've gone with the approach of saying, well, we're going to write a nice functional programming language, but we're going to opt in for treating everything as remote. So Erlang has no, it has the notion of processes. Those processes can be running at any VM. VMs can talk, but it doesn't, it doesn't treat anything as local. That's not to say that the implementations don't do things if it's local. So one of the huge problems with Erlang that's been highlighted in a paper called the Unified for Distributed Erlang Pitfalls and something else written by Hans Svensson is that, they have this problem where they say, well, if you send messages locally, it'll be synchronous, but if you send messages across the network, it'll be asynchronous. So you have this weird synchronous delivery again. It's not really said anywhere. It's in the implementation. And it's kind of like in some academic paper. They're like, that's not good, but like pretend it's not there. So they do a lot of like shortcutty things to make this stuff work. But they've opted in for this model to make it as simple as possible to treat everything as remote. Erlang has a very simple message passing semantic where you just you say process bang and the message. It just sends it across the wire and delivers it. And then it guarantees causal delivery somewhat based on network conditions and timeouts. It just does some somewhat causal delivery between pairwise processes. So you actually get like ordering guarantees and things like that. So it works hard to make this idea that you can opt in for remote programming not terrible. But they do make that decision. And you can argue whether that decision is right or not. The second one we'll talk about, so I'll actually go to the bottom and then I'll bounce up. So then we'll talk about Erlang-inspired languages. So there's a package in Haskell, if you're familiar with it, called Distributed Process. It's formerly known as Cloud Haskell, which was a project by Simon Marlowe before he went to Facebook. And I think that some of the Haskell stuff might share some of the distributed process work. And what the Haskell people did was that they took the unified semantics of Erlang, so that's actually not me saying that, that's the name of the paper. There's a paper called Unified Semantics for a Future Erlang. And it was the first time that the developers of Erlang kind of got together and wrote a paper about what the semantics of their language actually was, because the language had been developed in a lab and nobody really did anything kind of like, nobody really broke down the semantics. They kind of figured out what worked for Ericsson at the time, what would allow them to build phone switches and stay in business and things like that. So they basically reverse engineered all these semantics, didn't reverse engineer them, but inspected all of these things and wrote down a formal semantics for the language. And then the Haskell people basically implemented it, had to make some minor changes because Erlang does some weird things with message ordering and things like that can cause things to get a little hairy in Haskell. And this is a fantastic thing where you can do like distributed programming in Haskell, Erlang-style message passing, asynchronous message passing. One that you might be more familiar with than that is Akka for Scala, the Scala programming language. So this is done by the typesafe people. So Akka is another one that followed the Erlang paper. So Akka is an implementation of that. The ideas from that same paper with some different liberties. It's got some different performance characteristics than you would expect, given that the JVM is not as nice for the style of computation that Erlang does as the Erlang VM, because the Erlang VM relies on isolated heaps for fault tolerance. It relies on very, very fast scheduling of threads, and the Akka stuff kind of works on thread scheduling of like the lightweight green threads in Java. It's not really the same. Performance is slightly different, but still good. And then Akka has a variety of things like clustering utilities, a lot of those which have been inspired by React. So Akka Cluster and Akka CRDTs are implementations of things that we have in React, the database, to make distributed programming a bit easier. And so Bloom is a language by Peter Alvaro, who I mentioned at the beginning of this talk, and Neil Conway. Neil implemented the language. Peter implemented the data log variant that runs under the language called Daedalus. You can catch the Ulysses naming scheme through this. And what it is it's a logic programming for messages. Like you have lattices that are used as data flow variables. That are used for data log, these variables that accumulate messages. And what they do is they have, it's a temporal logic that the language is based on. So the only operators you have to interact with remote things, or even local things as well, is an asynchronous insert into a set, or asynchronous like push into a collection. That's your main programming operator, an asynchronous one. Then there's a delete one. We're not going to talk about that. And what's interesting about this is that this asynchronous kind of push into the set, this operator makes no guarantees on visibility. So the operator says, it will appear at a future time t. I'm not going to tell you when. If it's going across the network, it could be, you know, t prime, t double prime. If it's locally, it could be t prime. And you do have an operator for assuming something is local. But the major operator that you work with in the language says that you'll observe some fact, because it's a logic programming, so you observe facts. You'll observe some fact at a future time. So this is great because it enforces this asynchronous message passing and makes you think about, again, you're kind of opting into remote for a lot of it. But it makes, again, it doesn't make it as difficult as, you know, writing the networking code or writing like the partial failure rollback for your distributed transaction, right? And what they have is analysis tools to basically look at your program and say, hey, that part right there is something that you have to get everybody to agree on, because there's no way that I could possibly do that while ensuring state. And this is core to the idea of like the retraction of knowledge. You can't basically retract something without getting agreement, because you can have things get resurrected and facts observed that have already been deleted unless you insert coordination. And the language provides mechanisms for inserting coordination. You can say, I need some zookeeper, put my zookeeper right here. Cool. All right, so to end the talk, we'll end with a quote by Steve Panowski from that paper, which says, does developer convenience really trump correctness, scalability, performance, separations of concerns, extensibility, and accidental complexity? And his article argues no. Hopefully, I've done a pretty good job at convincing you no. But if I haven't, I'm happy to talk more. Thank you very much.
Great. So, and this is our first Papers We Love Boston, so let's just laugh about reading papers together.
Yeah.
Great. So it is about 8:30 right now. So we can kind of hang around here till 9, but generally at Papers We Love, at least in New York City, we kind of get like a group together, whoever wants to keep hanging out. There's several terrible Irish pubs from outside the city garden that we can attend. I'm sure they are empty with a couple of characters. So yeah, feel free. We've got some pizza left. Please eat it, because our fridge is just, there's no room. So eat the pizza and drink our beer, and we'll figure out a place to go, and we'll come hang out. But thank you so much for coming. If you want to speak, please speak. And if you're afraid to speak or like don't know, like please contact Bob or I, and we'll convince you that you're going to do an awesome job. So yeah, great. Let's hang out.